All right, so let's fully dive into proton NMR now. And we kind of introduced or looked at some of the differences already between carbon NMR and proton NMR. And so let's kind of look at some of the important skills that are needed for interpreting proton NMR. And you're going to see that a lot of these are very similar to carbon NMR. But just like it's important to find unique carbons for carbon NMR, we're going to do the same thing for proton NMR, finding unique hydrogens. We're going to use the same skills. We want to identify hydrogens that are in different chemical environments. This gets a little bit more complicated than carbons, and we'll see why in a little bit. But the exercise, the concept is still the same, and I can't encourage you enough to go through the homework problems, to go through practice problems, to check out your textbook, and work specifically on developing this skill. So let's start with one of these examples over here. So again, I'm going to use acetone as an example. And what I'm going to do in the beginning is just draw in the hydrogens here. After a while, you don't necessarily have to draw in all of them, but in the first go around, it's always a good idea um, to just draw them in so you can see everything. Now, I want to kind of give you a rule. It's not really a hard, like every works every time rule, but it's something that you should always keep in the back of your mind is that hydrogens on the same sp3 hybridized carbon are usually equivalent. Now, I want you to circle, highlight, star that word usually because there are going to be instances where hydrogens on the same carbon are not equivalent to each other. And we'll look at some of those examples on the next page. Okay, so let's take a look here back at acetone, and I'm going to start here. And what I'm going to do, I'll redraw this, and I'm going to draw every single hydrogen specifically. Okay, and I'm going to call these three hydrogens A. All three of those are equivalent to each other. A little tip, hydrogens on CH3s, always equivalent to each other. Um, and so all three of those are going to give the exact same chemical shift because they're all in the same environment. Now let's look at what that environment is. Okay, so attached to this carbon, I'll mark with the dot, there's a carbonyl and then another CH3. So we did this kind of exercise when we looked at carbon NMR. Now, if I go to the other side, for these three hydrogens, all three of those are equivalent to each other, but are they the same as A? Well, let's see if they're in the same environment. So this carbon here that they're attached to is next to a carbonyl, and that carbonyl has a CH3 as well. So it's the same exact environment. So I'm going to call these three hydrogens A as well. So acetone is only going to show one signal in proton NMR. Now let's take a look at the next example here. Let me fix this a little bit. So we got this dichloro compound. And again, I'm going to draw on the hydrogens here so we don't miss them. So there's a couple there, or one there, and then a few here. And just by looking at the groups here, we can kind of tell that those two sets of hydrogens are not equivalent to each other. This is a CH3. All three of those hydrogens, all three of these here are equivalent to each other. And this is a single hydrogen that's much closer to the chlorines than the other ones are. Now, I know this isn't part of the problem, but if I were to ask you, which of those two hydrogens or sets of hydrogens would have the higher chemical shift, what would be your answer? And you might think off the bat, well, wait a second, we haven't talked about chemical shift with proton NMR. That's kind of not fair. It operates on the same exact principle as carbon NMR did. And so you're like, well, okay, well, now that I know that, I might not know the specific values yet, but I know that since B is right next to two chlorines, highly electronegative atoms, it's going to have a much higher chemical shift than A. So the chemical shift for B is going to be much higher than the chemical shift for A. And again, we don't know those numbers yet. We will. We'll look at them. But we know that just based off of the trends, that we would see two signals and that B would have the higher chemical shift than A. And then let's look at this last one. So again, I'm going to draw all these hydrogens in. So there's three there and three there. And then there's, I'm just going to fix this one. And then one there. Okay, so I'm going to start here on the left. I'm going to call these three hydrogens A. Hydrogens of CH3s are always equivalent to each other. Now, does that automatically mean every single CH3 here, or hydrogens on a CH3, are automatically equivalent? That may or may not be true. You can't just assume, well, just because it's a CH3, all CH3s are equivalent. For example, if I go to the other side here and I have those three hydrogens, all three of these are equivalent to each other, but they are much closer to the thing that to this oxygen than the A hydrogens are. So those will have a different chemical shift because they're in a different environment. But if I go to these these CH3s over here, or this one over here, we notice that they're attached to the same carbon as the A ones are. So I'm going to call these A as well. And then the single hydrogen here attached to this carbon, I put a dot there. That is unique. I'll call them C. And these two hydrogens here, I'll call D. All right, so these would have four signals. And if I were to, again, just to kind of do the same exercise as before, which of these do you think would have the highest chemical shift? So you're looking for hydrogens that are next to more stuff, and especially if it's electronegative. So notice that D and B are both adjacent to an oxygen, a highly electronegative atom. So let's focus on D and B. What do you think between D and B would have a higher chemical shift? Well, D has more stuff around it. Not only does it have an oxygen on one side, it's got a bunch of carbons on the other side. B just has that one oxygen there. So they'll be close to each other, but since D has more stuff, its chemical shift will be slightly higher. And so then let's compare A to C. Which one do you think between A and C would have a higher chemical shift? Well, you could look at it a couple ways. C has a lot more stuff around it, as well as it's closer to the oxygen than the A hydrogens are. So C would have the next highest chemical shift, and then A would be the farthest upfield. And again, we'll talk about chemical shift and numbers in a little bit, but you can use the same exact trends that you used for carbon NMR. Now let's talk about some more complex or difficult examples. First of all, dealing with rings. Rings get a little tricky when we're trying to identify unique hydrogens. And again, sometimes it would help to draw them all in. So I'm going to start with this. I'm just going to draw all the hydrogens in. Now, one of the things you can do is see if you can identify any symmetry, because that will simplify the problem. And notice that if I cut this molecule in half, the left side looks exactly like the right side. So let's start with these two hydrogens here. Now, those two hydrogens on the same sp3 hybridized carbon. And as I said before, they're usually equivalent. But right now, take my word for it, they are equivalent to each other. So those two A hydrogens have the exact same chemical shift. Do you see any other hydrogens that are in the same exact chemical environment? I cannot call these A hydrogens because they're farther away from the carbonyl. But these over here are related by symmetry. And one way you can kind of look at this is if I were to turn the molecule over, I'd have the exact same thing. So what I will call these hydrogens, I'll start calling them B. And just like with the A hydrogens, these over here are related by symmetry. And then these two hydrogens here, I'll call them C. So this would have three signals. Now let's look at another ring example. This time I'll use a benzene compound. And I'm going to draw in all the hydrogens just to make it a little simpler. As I said, after you do more and more examples of these, you won't have to draw in the hydrogens, but in the beginning, I highly recommend it. Okay, so let's start with the CH3, the benzylic hydrogens here. So all three of these are unique or are equivalent to each other. They're on the same sp3 carbon. And let's just kind of go around like clockwise from there. This is obviously going to be different. It's attached to benzene. Can I say that that's true for all the other ones because they're attached to benzene? Can I call all the rest of them B? No, I can't. They're not in the same environment because the B hydrogen there is the only one that's between both a methyl and a chlorine on the benzene ring. And that means this one here is unique. It's next to a chlorine, but it's not next to the methyl. So that's why I can't call B and C the same. And I'm kind of using the chlorine as like a locator because as I go to the next one here, I know D is not equivalent to C because it's farther away from the chlorine. And I can say the same thing with this one. With E, it's farther away from the chlorine and closer to the methyl than D or C is. All right, another type of complex or difficult example are dealing with alkenes. And the reason alkenes are um, somewhat difficult is because you cannot rotate around a carbon-carbon double bond. All right, and if you don't believe me, build a model kit of an alkene and try to rotate that double bond around. You have to break your model kit in order to get that to rotate. So the effect of that is that sometimes you can have hydrogens on the same carbon that are not equivalent to each other. And I want you to look at this one on the left here. Okay, so let's just kind of start with the easy one. We got a CH3 here. Those three are all equivalent to each other. There's no other CH3s around, so I don't have to worry about that. But when I go to the two hydrogens on the other side of the double bond, I'm just going to start by calling this one B. Is B exactly the same as the one right below it? You say, well, it's on the same carbon. But so I want you to think about the fact that you cannot rotate a double bond. And what that means is that this top hydrogen is stuck looking at the methyl group. It does not get to rotate around and say hi to the chlorine. And we'd say the same thing is true for this bottom hydrogen. It's stuck looking at the chlorine. And it never gets to rotate upwards and be on the same side as the methyl group. If we could rotate around that single bond, or if it was a single bond and we can rotate it, then yeah, those two hydrogens would be equivalent. But we can't rotate that bond. And so B is stuck looking at the methyl group, and C is stuck looking at the chlorine, and they never get to see anything different. So this is an instance where hydrogens can be on the same carbon yet not be equivalent to each other. Each of those, the B hydrogen and the C hydrogen, would have their own unique chemical shift. So we would see three signals for this compound. Now let's compare that to this one. And let's start at the same place. Let's start with the CH3s. Okay, so all three of these are equivalent to each other. They're on, remember, hydrogens of a CH3 are always equivalent to each other. And can I say that these down here are A hydrogens as well? Well, if I look at it, they're attached to the same carbon, or the carbon, those hydrogens are attached to the same carbon of that double bond. So those, in fact, will be equivalent to each other. Now, if I'm going, I don't want to necessarily like hang on the trend of the first problem we did, or the previous problem, I should say. And if I call this B, I need to look and see what, you know, B is always looking at. B always gets to look at the methyl group up top. Well, what is the bottom one looking at? The bottom one's looking at the exact same thing, a methyl group. And so in this case, even though the rotation around that double bond is restricted, they're both equivalent because they both see the same thing. They both see a methyl group. And so they are this time equivalent to each other. So this one would have two signals. Now, probably one of the most, the trickiest ones are dealing with compounds with stereocenters. So let's draw this out. And I'm going to draw all these hydrogens here. And there's a reason why I'm giving those two hydrogens like some stereochemistry. Because when you have a chiral center and you have CH2s, you have to do a little mental exercise or write it out. You know, it might be helpful to write it out in the beginning. But what you need to do is imagine replacing, and I'm going to label these for the sake of argument. I'm going to call this one A and this one B. What you need to imagine is replacing A with a random group. I'm just going to call it G. So if I do that, then I get this. Now I'm going to do the same thing. Replace B with the same random group. And I want you to look at those two things and tell me, what is the relationship between these two structures? They're diastereomers. If you do this exercise and you replace one hydrogen with a group and then the other hydrogen with a group, and you get diastereomers as a result, we call those two hydrogens, A and B, diastereotopic. And I need you to pay close attention to this. Diastereotopic hydrogens are never equivalent to each other. And so the A and B hydrogens there are in fact non-equivalent. They each have their own unique signal. Now, I'm not going to, or I don't have to worry about doing this with the CH3s, but just for the sake of this exercise, let's do this with one of the CH3s here. So let's redraw this. We've already said that those two hydrogens that have the stereochemistry are not equivalent, but let's pick a CH3 over here and let's replace one of them with a random group. So I just put a random group there. And did I make a new stereocenter by doing that? No, it's still not chiral. So I don't really care. I can replace one, two, or one hydrogen, the second one, or the third one with a random group, and I still don't make anything new. And so we call these types of hydrogens homotopic, which are always equivalent to each other. That's why I was saying earlier, hydrogens that are of a CH3 group are always equivalent to each other. A CH2, though, that you kind of have to do this mental exercise. So if it's diastereotopic, those hydrogens are not going to be equivalent to each other. Now let me introduce one more type of hydrogen here. And I'm going to focus on these. You say, okay, well, there's no stereocenter there. Well, just for the sake of exercise, I'll call this one A and this one B again. Let's do the same exercise as before. Let's replace A with a group. And then let's replace B with the group. And what do you notice about the relationship between those two compounds? They are enantiomers. So we call those two hydrogens enantiotopic. And the end result is that enantiotopic hydrogens are always equivalent. So the simple thing to look at is that if you have a chiral center like this, and you got a CH2, those CH2 hydrogens are going to be diastereotopic. And diastereotopic hydrogens are never equivalent to each other. Other than that, if they're homotopic, we don't care, always equivalent. If they're enantiotopic, we don't care, they're always equivalent. It's only this instance of where they're diastereotopic, where they're not equivalent to each other. So in the next video, we're going to talk about chemical shift. And again, I'm going to break it down just like we did with carbon NMR and look at it in terms of regions.